Cisneria Engineering, Spain, and Hypothalamus Artificial Intelligence, USA. Cisneria Engineering and Hypothalamus I have agreed on a technology alliance to jointly provide services to the special transport sectors, based on highly complex mathematical models. The technological capabilities of the two companies, in artificial intelligence and mathematical programming, make them ideal partners to face the multiple challenges that exist in advanced analytics applied to the transport sector. Due to the experience of the two companies, this alliance is particularly strong for the optimization of special transport systems such as the aviation industry, planning and operation of ports and rail systems, mathematical programming in the transportation industry. Optimization-based applications cover industries and mathematical problems in all sectors. The table, developed by IBM, presents the most familiar applications in several sectors. The travel and transport sector stands out. The main optimization-based applications for the travel and transportation industries: workforce management, crew and drivers planning and scheduling, and staff rostering and scheduling; fleet management, fleet planning and dispatching, network planning, and timetabling; asset management, airport and terminals resource allocation, crane scheduling, and warehouse resource scheduling; yield management, pricing, and dynamic packaging. The table presents some examples of optimization cases in the aviation industry. The table presents some examples of optimization cases in the railway industry. The table presents some examples of optimization cases in the port industry. Applications of operations research in railway sector. Mathematical models cover the entire hierarchical chain of decisions, strategy, tactics and operations. Below are real-world use cases, along the decision-making chain, across the multiple business that make up the railway industry. Economic value added by optimal planning and scheduling in railway operations. Deutsche Bahn, the largest European railway company, is moving more efficiently thanks, in part, to a new decision support system. The system optimizes train rotations in cargo, regional and long-distance passenger transport divisions. The changes have resulted in direct savings in addition to better planning and productivity. The productivity of the locomotives and railcars has increased up to 10%, while the time savings were up to 80%. Metro systems. Metro de Madrid, Metro, optimization of staffing, train depots and lines. Metro needed better planning, knowledge and management of operations, to optimize resource scheduling, considering the large number of rules and limitations involved with labor policies, such as vested rights, shifts, breaks, union agreements, etc., and industry regulations. The planning must consider all the variables that have an impact on demand forecasting, such as weather conditions, vacations, breakdowns, seasonal variations, cultural and sporting events, etc. Using optimization software for scheduling, and real-time visualization for supervision, Metro has optimized in real-time two core business operations: staff assignment, and management of train depots and lines. Optimization software helps ensure that the 565 million riders Metro serves annually benefit from more responsive transit service and better managed operations. Metro has improved resource management, scheduling and adaptation of employee preferences, significantly increased efficiency in staff scheduling and train management, develop traffic plans faster and give passengers advanced traffic status, react faster to exceptional conditions, offering higher levels of customer satisfaction, and improve the quality and speed of decision-making. Netherlands Railways optimize the rolling stock allocation. Netherlands Railways, the nation's largest and Europe's busiest, 16.2 billion passenger kilometers by 2008, needed the ability to manage more trains and passengers within its 2008 infrastructure footprint. Netherlands Railways and IBM develop powerful algorithms to resource planning that can adapt scheduling and rolling stock allocations to short-term fluctuations in ridership. The mathematical tool was called ROSA, rolling stock allocation. With ROSA, Netherlands Railways can create an optimized operating plan that maximizes service quality, minimizes costs, and provides guidance for future infrastructure investments. The business benefits was $27.1 million in annual cost reduction, through the optimization of rolling stock allocation, incremental revenue gain of $54.2 million, through new approach to timetabling, 2% increase in on-time performance, shorter lead time for the development of new rolling stock allocation plans, and ability to accommodate additional ridership, growth with minimal new infrastructure investments. Société Nationale des Chemins de Fer Français, SNCF, optimize rolling stock maintenance scheduling. SNCF developed a scheduling of locomotive maintenance operations model, based on a mix of traveled distance and time. The system functions are: long-term scheduling for budget analysis, 1 to 2 years, medium-term scheduling for workload, 1 to 8 months, and short-term scheduling, 1 to 4 weeks. The benefit: the mathematical model allowed SNCF to save 10% of maintenance costs. Japan Railways East uses optimization for Shinkansen timetabling. The Shinkansen, colloquially known in English as the bullet train, is a network of high-speed railway lines in Japan. Initially, it was built to connect distant Japanese regions with Tokyo, the capital. Beyond long-distance travel, some sections around the largest metropolitan areas are used as a commuter rail network. The main features of the system are: dynamic replanning of the Shinkansen lines in case of an unexpected failure, recomputes a schedule that minimizes the total delays. Development of the optimization model took 1 year, and scheduling engine optimization solved the problem around 20 seconds, for 300 trains per day, on 4 crossing lines, servicing 37 train stations. The main benefit are: savings in total train delay time is up to 50%, and savings in recovery delay is up to 50%. The complete route and cargo allocation plan is composed of 3 operations research activities. Routing: given the demand for freight transport, from an origin to a destination, the set of operational policies, under which routes and cargo, will be assigned to trains. Blocking: the blocking policy specifies how blocks are built, at each classification yard on the rail network, where blocks, they are the set of wagons that are grouped, since they share some initial portion of stations in their route, although their final destination is not the same, and classification yard, they are nodes that belong to the railway network where the wagons are loaded, or unloaded, and classified, according to their destination, or assembly, and make-up policy, specify the list of potential blocks that can go on the output train. While blocking models indicate the route to be followed by the load, and the distribution of sorting work at network yards, routing and make-up models determine the routes, and frequency of trains, and the allocation of blocks to trains. Scheduling or timetabling: it is the generation of a schedule, which accommodates all train planning, satisfying the restrictions of the capacity of the railroad, and the yard. Problem of handling freight cars. It consists of the dynamic distribution of empty wagons in the network, so that the associated transport costs are minimized. Locomotive assignment problem. It is the assignment of the set of locomotives to the program trains, at the lowest cost, while satisfying the constraints of compactness, capacity, and maintenance. The mathematical models that can be supplied for typical operational decisions, that can be implemented in the long-haul rail industry are: DEM, expected demand for rail transport services. Block, optimization of the blocking process and assignment of wagons to trains. ETT, elaboration of timetables. ALT, allocation of locomotives to trains, and ACT, assignment of crews to trains. The paper, the Canadian Pacific Railway transform operations by using models to develop its operating plans. Presents the mathematical models developed by Canadian Pacific Railway, CPR, to operate its train system. Until 2004, North American railroads had traditionally practiced tonnage-based dispatch, operating trains only when they have enough cargo. As a result, their customer service and use of crews, fixed assets, locomotives and wagons were poor. CPR followed this policy. CPR map shows some of the 4,200 locations CPR serves. Because railways interconnect, much of CPR's traffic moves to, and from, other railways in the US and Mexico. In 2004, every day CPR received approximately 7,000 new shipments, from its customers going to destinations across North America and for export. CPR must route and move these shipments safely and efficiently through its 14,000-mile track network, coordinating these shipments with its operational plans, for 1,600 locomotives, 65,000 wagons and more than 5,000 train crew members, and consider capacity and storage space at 250 yards. CPR has 6,000 customers shipping via 20,000 distinct origin-destination pairs. In planning, it must also account for track maintenance windows, and connections with other railways. These vital connections account for 40% of CPR's business. The railway must manage and integrate a complex set of issues, and assets, efficiently, 7 days a week, 24 hours a day. CPR generates the company's operations schedule by changing from the tonnage-based route creation scheme, that is, dispatching a train every time there was enough cargo, to a system based on the generation of a route itinerary. The model is composed of 5 activities. Generate a traffic forecast, which reflects the requirements of each market segment. Design the blocking plan. Design trains according to the blocking plan. Use simulation to analyze yard operations, and loads on trains, for each of the days of the week, and times of day, and pass train programming to planning tools that develop cyclic locomotive, and work equipment plans. These tools use operations research approaches, such as an optimal block sequencing algorithm, a heuristic algorithm for block design, and time-space network algorithms, for planning locomotive use, and distributing empty cars. The implementation of mathematical models saved $170 million from mid-1999 through autumn 2000. CPR estimates that saved at least an additional $119 million during 2001 and 2002 in fuel and labor costs alone. Current American dollars of the year 2004. Labor productivity, locomotive productivity, fuel consumption, and rail car velocity was improved by 40, 35, 17, and 41%, respectively. Furthermore, CPR now provides its customers with reliable delivery times, and has received many customer and shipping association awards for its improvement in service. CSX Railway uses operation research to cash in on optimized equipment distribution. In 1997, CSX implemented the U.S. rail industry's first real-time, fully integrated equipment distribution optimization system, the Dynamic Car Planning System, DCP. In 2010, CSX's railway's 21,000-mile network spans most of the eastern United States, and connects to other railroads to provide service over all North America. Before DCP, decisions about which empty cars to deliver to which customers were made locally, because there was no timely and accurate centralized data. The distribution of empty cars is complex. Every day, hundreds of CSX customers order hundreds of wagons. The source of the cars is a fleet of 90,000 cars, such as freight cars, gondolas, and hoppers, in a network with thousands of geographic locations. DCP tries to find the best empty car for a customer order, with best established by multiple cost and customer car preferences and service requirements. The problem has hundreds of thousands of possible solutions, and the constantly changing conditions exacerbate it. Throughout the day, equipment availability changes as customers return empty cars, and send new and updated car orders, and CSX disconnects cars for cleaning or maintenance. Unfortunately, dedicating equipment to a customer harms the use of the car. For example, international movements, between Mexico and the United States, of empty cars in opposite directions are clearly inefficient. Each day, CSX allocates hundreds of empty rail cars among hundreds of customer car orders using DCP. DCP seamlessly integrates operations research modeling into CSX's process that assigns empty cars to customer car orders. CSX estimates that the DCP system saves the company more than $51 million annually, and has saved $561 million from its implementation through 2010. DCP has also provided $1.4 billion in capital expenditure avoidance, because of more efficient car allocation. Fewer railcars yield improved return on assets, and reduced congestion on the CSX rail network. Customer satisfaction has also increased because of improved empty car delivery. Public benefits include improved highway safety, reductions in congestion, pollution, and greenhouse gases, and reduced tax-supported road maintenance, thus saving an estimated $600 million. BNSF Railway optimizes wagon allocation and routing. BNSF is one of the largest freight railroads in North America. BNSF has 35,000 employees, 52,300 kilometers of track in 28 states, and nearly 8,000 locomotives. It has 3 transcontinental routes that provide rail connections between the western and eastern United States. BNSF trains traveled over 272 million kilometers in 2010. BNSF uses mathematical modeling for allocate railcars to customer demands, minimize empty travel distance, constrained by railcar type, railcar size, railcar status, and shipment dates and locations. Scheduling, every 15 minutes, on a 14 days time horizon, for 60,000 cars. The benefit for BNSF is that empty car miles are reduced by more than 6%. Optimization of locomotive planning. It involves the design and implementation of an optimization model for the assignment of locomotives to trains in circulation, considering the key characteristics of locomotives. The model must allow adjustments to be made to the allocation of locomotives for regular trains, and to generate new assignments in case of failed locomotives or additional trains. Challenge: automate the assignment of locomotives to already scheduled travel trains. Solution: design and implementation of an optimization model for the assignment of locomotives to trains in circulation, considering key characteristics of the operation of the system. It executes the assignment process periodically, scheduled, or manually, run the process at the request of the user, and by events due to an eventual abnormal situation. Develop and use the mathematical model in a proof of concept, POC, for Ferromex that operates more than 8,500 kilometers of railways and connects 5 cities along the border with the United States, 4 ports on the Pacific coast, and another port on the Gulf of Mexico. The POC was coordinated under a business partner agreement with IBM. Ferrocarril Mexicano, Ferromex, is a private railway consortium that operates the largest railway network in kilometers in Mexico. Ferromex is a Class 1 railroad according to the Association of American Railroads, AR. It began operating on February 19 in 1998, following the privatization plan of Ferrocarriles Nacionales de Mexico. It is a company that has its main activity in cargo transport, and only offers 2 tourist routes, Chepe and Tequila Express. This requires developing the offer of services in freight and passenger transport, which are different, since freight trains are dispatched on demand, while passenger trains are dispatched according to a timetable. The main products transported are agricultural products, automotive, cement, energy, petroleum products, and metals and minerals. The type of operations are intermodal, offers intermodal transport of goods in containers and semi-trailers, with different scopes, and industrial products, includes the largest number of customers and products that use the company's services, which can be grouped into the subsegments: food, beverages, sugar, paper, cardboard, forest, electro-domestic, etc. The mathematical model implemented by HI was used during the POC to optimize the route Mazatlan, Tepic, Manzanillo, Guadalajara and Irapuato. The modeling was carried out by dividing the route into 4 sections, linking the main cities, or train stations. Several trains flow in each section. A train is defined as a set of locomotives and wagons. Each train has its arrival and departure times to the train stations. Each train is assigned the cargo it must carry. Each section is divided into stretches. Each stretch, or link, is associated with an average slope, which implies differences in energy consumption. At any of the points, nodes, that limit the stretch, locomotives can be incorporated or disincorporated. Locomotives can travel on the train, turned off, only to transport them to a node, where they must come into operation, and in operation, pushing the train. The fuel consumption of the locomotive must be considered, according to its energy productivity, which depends on the slope and load. The mathematical model must determine the nodes in which the locomotives are connected, or disconnected. All physical laws of the rail system must be satisfied, such as maximum load, maximum speed, energy consumption, train displacement, displacement of locomotives, availability of locomotives, and material balance. The main results of the mathematical model are: locomotive assignment scheduling corresponding to each locomotive, according to the train to which it is assigned. Summary of maneuvers indicates the periods when locomotives are loaded, or unloaded, to trains on the route. Availability of locomotives by period indicates the location of locomotives when they are not assigned. Gantt visually presents the location of the locomotives. The table presents the summary of the assignments to the trains, indicating the stretch, and the status, on or off. The graph presents the availability of locomotives stopped at stations. The Gantt presents the connection of locomotives to a train. In this case, 8 trains are presented. The Gantt presents the connection of locomotives to a train. In this case 3 locomotives and 1 train, the or my Ms, are presented. Optimized workforce management. Transport industries face itinerary disruptions, vehicles delays, and daily cancellations due to unexpected events, including inclement weather, mechanical problems with vehicles, such as aircraft, trains, buses, and ships, and unavailability of crews. As a result, crews may find themselves in the situation of not attending their scheduled operations. The transport companies must quickly reassign crews to cover available pre-scheduled operations, and return them to their original schedules, in a cost-efficient manner, while meeting government regulations, contractual obligations, and quality of life requirements. The main problems in workforce management: staff sizing regulation, rostering, timetabling, task assignment, and monitoring and control. Energy savings in train control optimization. The need for a clean environment is based on a rational consumption of energy. This covers all industries, and in general all human activities. Optimal train travel speed planning involves mathematical modeling to minimize energy consumption when the train has a predefined maximum arrival time. First, it must be considered that all industrial processes are variable speed, and that energy consumption, depending on the speed of the process, is nonlinear, it is exponential. This implies that, in the absence of economies of scale, the regulation of the speed of industrial processes is fundamental in the process of controlling energy consumption. Production facilities do not have a defined capacity, it is set according to the speed of the process, and the time that this speed lasts. That is a decision variable of industrial operations. The table presents the energy consumption versus speed of the AB 103 high-speed train. The column 2 shows the kWh consumed per kilometer for 3 speeds analyzed. The nonlinearity is noticeable. As a vehicle increases its speed, when it is operating above its maximum efficiency, the unit amount of fuel consumed increases, which implies higher variable costs. However, increased speed means increased production capacity, which lowers investment costs due to increased vehicle use. The optimal decision is not obvious. The paper Optimal Trajectory Planning for Trains Using Mixed Integer Linear Programming presents a mathematical model that includes, in detail, the resistance of the route, such as slope, tunnels, and curves, and arbitrary speed restrictions. The objective function is a weighting between energy consumption and driving comfort, but it could be minimizing the cost of energy. The nonlinear function of energy consumption versus velocity is represented by a piecewise linear function. The optimal control problem is formulated as a mixed integer linear programming, MILP, problem, which can be efficiently solved by existing solvers. The case study considered two cases. For the first one, the total running time equal to 5.25 minutes, indicated by T1, black solid line, while for the second case is 10 minutes, indicated by T2, red dashed line. The speed of the train is presented in Figure 1. The optimal reference trajectories and the tensile and braking forces applied are shown in Figure 2. The energy consumption with running time T2 is lower than that with running time T1, but at the cost of a longer travel time. Figures 3 and 4. It is worth to note that the computation cost is very low for this MILP approach, is less than 10 minutes in 2011. Today the algorithm must be, at least, 1,000 times faster. The figure, extracted from another study, presents the relationship between the energy consumed and the travel time. The nonlinear behavior of the function is evident. The train journey can be modeled as an interleaved sequence of three states. Braking, when the train slowed down, eliminating energy consumption or recovering previously consumed energy, which can be used later, green line. Dwelling, when the train maintains a constant speed, minimizing energy consumption, and accelerating, when speed is increased, and energy is consumed according to the situation, red line. Railway alignment optimization. Railways are threatened by geological hazards, whose disastrous effects include severe economic losses and serious casualties. It is vital to properly consider these hazardous geological impacts during a railway alignment optimization process. However, geological factors are complex, especially in mountainous regions. In addition, economic factors are also crucial in the design of the railway alignment. Therefore, optimizing railway alignment can be termed a bi-objective decision-making process, cost versus risk. Geological railway alignment implies the analysis of design criteria for three typical geological hazards: debris flows, landslides, and rock slides. Geological railway alignment optimization models include spatial geological constraints and geological risk assessments. Geological hazard assessment includes geological susceptibility and vulnerability assessments. Therefore, the lowest cost alignment must be discovered to build a bi-objective cost-risk model. Alignment search processes are also improved to solve the proposed model by integrating geological constraint management approaches and bi-objective alignment optimization. Artificial intelligence models can produce less expensive and safer solutions than the best alignment designed by experienced human designers, while meeting all required design standards. Like Herbert Simon, Hypothalamus AI believes that the computer-based mathematical modeling is the greatest invention of all times. Thank you for your attention.